You know, there's this powerful, invisible energy transfer happening all around us, every single day, from the ice cubes clinking your drink to the sweat on your skin. Today, we're going to pull back the curtain on the hidden energy that literally cools our world. Okay, let's start with a feeling we've all had, right? You hop out of a swimming pool on a super hot day, and for a second, you shiver. The air is warm, so what gives? Why that sudden chill? What is actually going on in that moment? Well, the answer is a fascinating process of invisible energy transfer. And to really get it, we're going to do something fun. We're going to shrink ourselves down and follow the incredible journey of one single water molecule as it goes from a solid to a liquid to a gas. All right, so our molecule's journey starts off in the solid state, locked away inside a crystal of ice. This is stage one, the big melt. So picture this. Our little water molecule is part of an ice cube. And it's not just sitting there, no way. It's constantly vibrating, kind of shaking in place, but it's held super tight by the forces of all its neighbors. Now let's imagine a super simple experiment you can probably picture in your head right now. We take some ice, we pop it in a beaker with a thermometer, and we start adding a little bit of heat. Now we're going to watch that thermometer very, very closely. Just like you'd expect, the ice starts to melt and turn into water, but here's where it gets weird. The thermometer? It is absolutely stuck at 0 degrees Celsius. I mean, we're pumping heat in, but the temperature just isn't moving. So that leads to the big question, right? We are adding all of this heat energy into the system. So why in the world isn't it getting any hotter? Where's all that energy going? Well, the answer is this amazing concept called latent heat of fusion. Latent literally just means hidden. So this is the hidden energy that the ice is soaking up. It's not being used to make the particles jiggle faster. That's what temperature measures, right? Nope. This energy has a special job to overcome those forces of attraction and to literally break the bonds holding that crystal together. Okay, so our molecule has broken free. It's now flowing around as liquid water, but its adventure is far from over. The next big transformation is right around the corner, the big boil. Now that it's a liquid, our molecule has way more freedom. It can zip around, bump into its buddies, and as we keep adding heat, it just gets more and more hyped up, gaining kinetic energy and moving faster and faster. The temperature keeps climbing until, wait a minute, this sounds familiar. It hits 100 degrees Celsius, the boiling point of water, and bam, the thermometer freezes again. It's stuck. The water is going crazy, boiling like mad, but the temperature refuses to budge. So what's going on this time? Well, this is the latent heat of vaporization, and this is a huge amount of hidden energy. It's the final power-up our water molecule needs to absorb to make the final leap, breaking completely free from all its neighbors and launching into the air as a gas, what we know as steam. But here's the thing, boiling isn't the only way for our molecule to make its great escape. Nope, there's a much quieter, more common way this happens all the time. Let's look at the silent escape, evaporation. I mean, think about it. Does water always have to hit its boiling point to turn into vapor? Of course not. What about a puddle on the street after it rains? It doesn't boil away, does it? It just disappears. So what's up with that? That, my friends, is evaporation. And unlike boiling, it's what we call a surface phenomenon. Basically, at any temperature, a few lucky particles right at the top of the liquid have just enough oomph, just enough kinetic energy to break free and float away. Okay, so let's break this down because the difference is key. Boiling is a party. It's fast, it happens everywhere inside the liquid, but only at one specific temperature. Evaporation? That's more like a slow, silent escape. It only happens at the surface, it's way slower, but it can happen at any temperature. And what's cool is we can totally speed up this silent escape. You spread your wet laundry on a clothesline, bam, you've increased the surface area. A hot sunny day, that's an increase in temperature. A nice breeze, that's wind speed carrying the vapor away. And if the air is dry, low humidity, it's like an empty bus ready to pick up more water vapor passengers. All these things make evaporation happen way faster. So, okay, melting, boiling, evaporation. Why does any of this really matter in our day-to-day lives? Well, because this hidden energy, especially the latent heat of vaporization, is basically a super powerful natural cooling engine. Let's look at how we put it to work every single day. And this takes us right back to where we started, that chill you feel getting out of the pool. Or let's put it another way. Why does our body's own natural air conditioning system, sweating, actually cool us down? It is all about that latent heat of vaporization. As that liquid sweat on your skin evaporates, those escaping particles need a lot of energy. And where do they get it? They steal it, right from your skin. They are literally carrying your body heat away with them as they escape. That's why you feel cooler. It's incredible. All right, here's a final brain teaser for you, and this really highlights the power we're talking about. You've got boiling water, and you've got steam. Both are at the exact same temperature, 100 degrees Celsius. Which one is going to give you a worse burn? And this just brilliantly illustrates the power here. The answer is steam, by a long shot, and now you know why. Each one of those tiny steam particles is carrying a secret weapon, that extra hidden payload of latent heat of vaporization. So when it touches your skin, it delivers a nasty 1-2 punch. First, it releases that massive amount of hidden energy as it turns back into water. Then, it burns you as regular old 100-degree water. It's just way, way more powerful. And this whole principle is at work all around us, in things like desert coolers or even just a simple clay pot of water. So the next time you feel that shiver after a swim, you'll know exactly what's happening. It's the price of admission for millions of tiny water molecules making their great escape. So now that you're in on the secret of this hidden energy, where else do you see its cooling power at work?